Polar, non-polar, guys. We've talked about them. It's a review. Which one, Bella? Yeah, polar means unequal sharing, so the non-polar would have to mean equal sharing. Absolutely. So we've talked about that, like I said, back in Unit 4. But we talked about it with just a bond, one bond, between two different atoms. We looked at their difference in electronegativity values. All right, if it was greater than 1.7, we knew it was an ionic bond. If it was between 0.5 and 1.7, it was polar. If it was less than 0.5, we consider it to be nonpolar. But now we're going to apply the same idea to an entire molecule. All right, so we've been drawing structures for the past week or so. We had our quiz on it, which I'll pass those back here in a few minutes. So now we're going to talk about the sharing that's taking place within a molecule. All right, and that's what polarity leads us to. So polarity of molecules, guys, it's directly related to the shape of our molecule. All right, it's directly related to the shape of the molecule. It determines many of the properties of the substances. Does it have a high or low melting point or boiling point? Those types of things is what the polarity will allow us to. So in order for us to understand or know the polarity, be able to figure it out, what do we have to know? We have to know the shape. We've got to know the shape, which is why we've waited to do polarity till now. So polarity, guys, we need to know first the Lewis structure and then the Vesper geometry. Everything we've been doing so far, you're still going to do. You're going to draw the structure. You're going to figure out the Vesper geometry, bent, linear, trigonal planar, tetrahedral, all right, trigonal pyramidal. Then we're going to, once we have the structure and we know the shape, all right, we can then determine its polarity. So here's the deal. Symmetrical is usually nonpolar, but the satellite atoms have to be the same. That's the key here. So I encourage you guys to be writing notes and doing what I'm doing here. Satellite atoms have to be the same so they cancel each other out. If they're not the same, what do you think it's going to be? What? Asymmetrical, which would mean polar, guys. Right. Non-symmetrical then is polar. So if the atoms on a symmetrical molecule are different, it will be polar. Typically, though, they are non-polar if they're symmetrical. Non-symmetrical or asymmetrical, then we have polar where they do not cancel each other out. All right. So polar would be non-symmetrical. They don't cancel each other out. All right. They do not cancel each other out. So you've got to have your shape drawn correctly. This is where some of us drew bent molecules, like, for example, water. Some of us drew like this. If we didn't redraw it, that looks pretty symmetrical right there. All right, if I were to draw a line right down the middle and I fold it over, it's the same on both sides. They're mirror images. If I drew a line like this, it would also be symmetrical, same on the top and the bottom. But water, guys, is not symmetrical. It's not nonpolar. Is that right to say? Yeah, it's not nonpolar. That's okay to say. That's not a double negative, right? Okay, good. It's going to be a polar molecule, guys, because it's really drawn this way, is the actual shape of a water molecule. Because those lone pair electrons over there on the oxygen atom pushes it away. Therefore, when we draw the lines, it's not symmetrical either way you draw it. All right, and that's what we're going to get into here. So when we talk about Vesper geometries, guys, symmetrical shapes, these are typically nonpolar. All right, doesn't mean they are always nonpolar. You've got to know and remember that the surrounding atoms have to match in order for them to be nonpolar. But linear, trigonal planar, tetrahedral, those typically are nonpolar. They are typically nonpolar. So when on your test or on your quiz or whatever, all right, comes your way, you figure out, oh, I've got a linear shape or trigonal planar or tetrahedral, you've got to take it one step further. You can't just assume they're linear. You've got to look at what elements are surrounding the central one. If they're all the same, it's going to be nonpolar. It's symmetrical. But if they're different, that's when it will be polar. All right? If not, then they are polar. So if we talk about asymmetrical geometries, both bents are asymmetrical, trigonal pyramidal. All right? If the surrounding atoms don't match, it's polar. You got to remember that right there. All right, if the surrounding atoms don't match, doesn't matter what the shape is, it's going to be polar. All right, these ones are always polar, always polar. All right, any bent, any trigonal pyramidal, guys, they are always polar. So now when we draw our shapes, I didn't have you do this on your quiz the other day, but you have to draw your final shapes to reflect the geometry that it is. If it's trigonal pyramidal, you can't just draw it as a T. All right, you can't just draw something like this. You've got to draw it so that it looks trigonal pyramidal. The H's get pushed down away from those electrons. You can draw your first one like this, guys, but once you identify what the geometry is, your final structure has to be drawn to the best of your ability to make it look like it's three-dimensional, right, where it's pushed down. Obviously, that doesn't look like, oh, you can't see that's a pyramid there, but that's how we draw it to show that it is. Tetrahedral, something like carbon or methane, carbon tetrahydride, would look something like this. All right, that's what it looks like when we draw it as a molecular shape. The pictures on your packet in that chart on page 2 show you what the shapes look like. All right, we're going to practice that more on Monday. So, let's do some examples. Water, carbon dioxide, and HCN. Go ahead and draw your structures first, determine the geometry, and then we'll talk about the polarity. Give you guys a couple minutes. All right, so when we look at our structures with our Vesper geometries, this is what we get. Now, when it comes to polarity, guys, so anything that I have here on the screen right now is nothing new. We've done this over the past week and a half. The new piece is the polarity piece. So, we're looking for symmetry. Symmetry here. So that means when I draw a line, or if I hold up my ruler like I'm doing, it's got to be both ways, in the X and Y axis. So here we go. The first one with water. We draw a line across it. Is that symmetrical? No, if it's not symmetrical in one of the axes, folks, it's not symmetrical. This one, water, it's not symmetrical either way you look at it. Therefore, it's asymmetrical, so what's the polarity going to be? Polar. Asymmetrical means it's polar. Carbon dioxide, we do the same thing. Draw your lines if you need to. Is that symmetrical? Absolutely. Is the Y symmetrical? So what would this be? This is non-polar. You can abbreviate it, guys, as just P and NP if you want to. That's fine with me. I know what you mean. Okay. Again, it's non-polar here with carbon dioxide because why? Same elements on both sides. It's the same. So they're pulling the same amount. HCN. If we take a look at it. Actually, let me go back. This way, is that symmetrical? Absolutely. When I draw a line like this, it's symmetrical. Same on the top and the bottom of the line. But when I draw it this way, is it symmetrical in the y-axis? No, you've got different elements here, guys. You've got to look at both axes when you're looking at polarity here. So this, in fact, would be polar. It would be polar. All right. Asymmetrical, it's polar. Symmetrical, it is non-polar. Any questions with these examples? You will have to do this on your lab today, and you will have to do this on your test on Tuesday. Questions? For the sake of time, we're going to skip over intermolecular forces right now. We'll talk about those on Monday. We're going to get to our lab.